this is basically the end of the course. So before going, let's make some conclusions. So if you remember this slide, the path that we had to undergo in these 5 weeks, we started from very fundamental notions in metric geometry. We also spoke about Riemannian geometry, which were actually the theoretical foundations for our models of shapes. Then we discussed numerical geometry, how to approximate the shapes, how to measure distances using fast marching algorithms. So this provided us something to use these theoretical models in practice. We spoke about optimization problems, which were used then in multidimensional scaling, spectral embedding, basically everywhere. We talked about non-Euclidean embedding, generalized multidimensional scaling problems. We mentioned the isolating invariant distances that we call Hausdorff distance, and then spoke about different applications, including correspondence problems and phase equation. So, as I mentioned in the introduction, this course is about common denominators. We try to put common denominators. So it's maybe not a single common denominator, but actually 3 pillars on which our non-rigid world stands. So the first pillar is metric geometry. This is basically, this is the theory. This is the model of our shapes. Numerical geometry is basically the practical implementation, something that allows us to represent these models in practice, something that can be represented using a computer. Finally, optimization is something that allows us to make computations, something that allowed us, for example, to compute distances between shapes or compute correspondences. So, if I had a very short piece of paper on which I would like to write messages that we would like you to take home, let's limit it to 3 messages. So, what is the first message? First message is that we can consider shapes as metric spaces. This was basically the common denominator of this course. Everywhere we consider shapes as this or that metric space with different selection of the metric. Second message is isolating invariant similarity. We wanted the distances between shapes which are invariant to some class of transformations. So we said, let's make the shape similarity invariant to isometric transformations. Now, isometric in the sense of some metric, and we've seen different ways to define the metrics, and this is actually another common denominator. This is basically a generic framework that allows us to address different problems, different classes of shapes, and we've seen, for example, that both non-rigid and rigid shapes can be regarded in the same way, in the same framework, just defining different metric. We use the Euclidean metric or we use the geodesic metric for non-rigid shapes. Final message, the message of today's lecture about correspondence problems. Basically, if we solve the correspondence problem, we get the similarity problem free of charge, and vice versa. Basically, these 2 problems are interrelated. So there is also common denominator. Different algorithms such as multidimensional scaling or generalized multidimensional scaling can be used for both problems. So these are the 3 messages. At this point, I think I will thank you for your attention. And of course, all the thanks go to Davide for organizing this great opportunity for us. I must say that we enjoyed it a lot. Thank you very much. Now,
maybe some feedback.
Now feedback. We want to hear